Okay, so we use Ka to talk about the strength of a weak acid, right? So the greater the Ka, the stronger the acid. Now, another way that we can describe it is percent ionization. Now, if you guys remember, weak acids, they don't dissociate completely, right? Only some of it dissociates. And so we can talk about it using Ka or percent ionization, which talks about the percentage that acid dissociates. So we have the formula right here. Where is it? Right here. And the formula is read like this. Percent ionization is equal to the concentration of H plus at equilibrium on the top divided by the concentration of the acid initial. Now keep these subscripts in mind that the top is at equilibrium and the bottom is at initial. So the original molarity of the acid, okay? And that's the part where you can get tripped up by this equation. So just make sure you guys keep that in mind, okay? The top is equilibrium, the bottom is at initial. Hey, Jaden, can you grade the physical ones for me? Sorry, I forgot to mention. Thank you. Okay, so percent ionization, we calculate it by the concentration of H plus at equilibrium and the weak acid concentration initially, okay? I'll log in for you later. Just leave it right here. Thank you. You can just start. Just the physical stuff. Yeah, just start. Oh, red pen's right there. Okay. Okay, so we got an example right here. So it's very easy to plug in the values. So we have a 0.035 molarity solution of HNO2. So this, we plug it into the bottom because this is the concentration of the acid initially. And then when we get the concentration of H plus at equilibrium, we just plug that into the top, which is why we get 3.7 times 10 to the negative 3 on the top, and then 0.035 on the bottom. Okay, so super simple. Just remember, top is equilibrium, bottom is initial. What is he playing? Dude, this floor has the weirdest people at this school. Yeah. Definitely not me, but everyone else here is really weird. Not a gamer. All right, so I'll give you guys a minute to try calculating the percent ionization for this. Doesn't he have a class right now? Is he playing trumpet? I'm sorry, guys. I can't play any instruments for you. Guitar. Oh, no. I'll dance for you guys. I'll break dance for you. Yeah, skip the articles. Just whatever's in the green binder. So maybe another 40 seconds to calculate percent ionization. Oops. Just leave it. All right, you guys ready to go? Okay, so when we calculate percent ionization, super simple. We put the concentration of H plus at equilibrium on the top. So we'll put the 4.2 times 10 to the negative 3 molarity on the top, divided by the original, concentration of the acid on the bottom. And then we multiply that by 100%. And that should give us an answer of 4.2%. Got that? All right, that's pretty much it. It just tells us that 4.2% of the acid molecules dissociated. The other 95.8% of them stayed together. So you can tell that for weak acids, most of it does not dissociate. Only some of the molecules dissociate. Okay, so this is kind of, I guess, an easier way for us to understand it, because 4.2 makes a lot more sense than, 4.2 times 10 to the negative 7. It makes a lot more sense for us to see it like this. Okay. All right. Any questions about percent ionization? Just want to go over it briefly. All right, let's move on. Okay, now we're going to get into the meat and potatoes of the unit, where we're going to be using everybody's favorite thing in the world, ice tables. Yeah, which has stoichiometry in it. Okay, so if we know the Ka value of an acid, and usually they'll give you the Ka value for a compound, we can calculate the pH using the Ka value. Okay, now we're going to do this just by going over a problem, 12.31, but I'm going to go through all the steps that you guys want to follow. So I do recommend at least writing down the steps, or at least knowing what the steps are, okay? Okay, so we have a problem. We're trying to calculate the pH of a 0.3 molarity solution of acetic acid. It's right here. This is a compound from vinegar. It's a weak acid. Okay. The first thing we want to do is write the ionization equilibrium. Basically, this is just telling us, hey, write the chemical equation. So we're going to write acetic acid, and it's dissolved in water, so it's aqueous. Okay. And I want you guys to do the equilibrium. I want you guys to write the products. So this is an acid, so it's going to dissociate and release H+. So I want you guys to take about 30 seconds, shouldn't take too long, to write the products of this equilibrium. Okay? Take about 30 seconds to do that. Alrighty, guys, so it shouldn't have been too hard. All we need to do is take out an H from this compound. So we're just going to write CH3COO minus. This is going to be the conjugate base. And then we're going to do plus H plus aqueous. And if you switch the H and the conjugate base, that's totally fine too. The position doesn't matter as long as these are the compounds we got. Okay? Yes. So it doesn't matter. You can put it first, you can put it second. The position doesn't matter because those are the two things it dissociates into. Yeah. If you switch them, that's perfectly fine too. Just keep the numbers in the right positions when you do the ice table later. Okay. All right. So number 2, the second step you want to do is use the equilibrium constant expression and the value for the equilibrium constant. So that just means write the Ka formula. Okay. So the Ka formula is the products. So CH3COO minus on the top, concentration of H plus divided by the concentration of the weak acid. And then we know that it is equal to 1.8 times 10 to the negative 5. So all we want to do is first write the equilibrium. Then we want to write down the equilibrium constant expression. That's step 2. Okay, so like I've been saying, we're not really doing anything new. We're just kind of combining it with the new stuff that we've learned in order to solve these problems. We already know stoichiometry, we know ice tables, we know equilibrium constant expressions. It's basically the same stuff, just kind of putting it all together. Okay. All right, any questions on step 2? Okay, let's move on to step 3. So once we got the equilibrium, and we have the equilibrium constant expression, what we're going to do now is we're going to write the ice table. So you guys can do this underneath your equilibrium constant expression, or not, sorry, not the expression, the equilibrium. But what we're going to do is we're going to do an ice table for this equilibrium right here. So I'm going to do ice. And then we're just going to plug in the values that we have. So if you guys want, you guys can take about a minute. I want you guys to plug in or try to fill out this ice table. Okay, if you want to just plug in the info that we started with, you can do that. But if you're a little bit more confident and you could plug in, if you could finish up the ice table, that'd be great too. So take about a minute to plug in what you can into this ice table. Alrighty guys, so if you guys are still plugging things in, feel free to do that, but I'm going to start plugging things in so that we can go over as many problems as we can during this unit. Okay, so for the initial concentration of acetic acid, you should have written 0.3 molarity because that's the concentration of acetic acid we started with. And then obviously for the initial, for the conjugate base and H plus, it's 0 because we didn't start with any, right? It's going to be breaking down now. If you look at the stoichiometry, everybody's a 1-to-1 ratio. That means we're going to lose some of the acetic acid and we're going to gain the same ratio for the conjugate base and the H plus. So for the equilibrium, the values that we have right now are 0.3 minus X, X, and X. Okay. So far, so good. Any questions on where we got those values? Okay. Now we're going to go to step 4 is we're going to plug in these values right here in this row into the equilibrium constant expression. And so if I plug that in, we can write that Ka is equal to what, 1.8, right? 1.8 times 10 to the negative 5 is equal to the top. This is X. This is also X. So that's going to become X squared divided by 0.3 minus X. Now, this looks like a quadratic problem, right? And technically it is, but if you guys remember the 5% rule, there are times where we don't have to do the quadratic formula. Okay, I don't know if you guys remember, but if this part right here, the exponent, okay, if the exponent is, what is it, less than 10 to the negative 4, we can 99% of the time assume that it's going to follow the 5% rule. Okay, so if if the exponent is less than 10 to the negative 4, we can assume that it's the 5% rule. What that means is we can ignore this right here. We can ignore the minus X because the change is going to be so small, it's not going to make a big difference in our calculations. Does that make sense? Do you guys remember 5% rule? So make sure you guys jot this down somewhere, star it, memorize it, get it tattooed. Just make sure you guys have this somewhere because it'll save you a lot of time. You guys don't need to use the quadratic formula. So if the exponent is less than 10 to the negative 4, you can assume the 5% rule. We can get rid of the change. Okay. After that, this becomes a very easy algebraic problem. We just need to move the 0.3 to the other side. So on the left side, we'll have 1.8 times 10 to the negative 5 times 0.3 equals X squared. And then this is going to be step 4, sorry. Okay, so I'll give you guys maybe about a minute. I want you guys to finish out this problem, try to solve for X. And then if you feel confident, step 5 is just finding the pH. So if you guys want to try that step as well, go ahead. But no need, I'll go over that in just a minute, okay? Don't feel rushed. We're going to have a lot of practice problems with this concept. Alrighty, guys, finishing up your calculations, feel free to do that, but I'm going to start going over the answer. So on the left side, we're just going to do 1.8 times 10 to the negative 5 times 0.3. That should give us a value of 5.4 times 10 to the negative 6. Okay. And then if we want to isolate X, we just need to find the square root of both sides. And then if we find the square root, we should get a value of X is equal to 0.00232, or you can write this as 2.32 times 10 to the negative 123. Everyone got this? Okay, so that's step 4. That allows us to solve for X. And then last thing we need to do is calculate the pH. Now we can see that the value for H at equilibrium is just going to be X. So we know that the pH formula is the negative log of the concentration of H plus. So all we need to do is take this value right here for X and plug it into the pH formula. So it's going to be equal to the negative log of 2.32 times 10 to the negative 3rd. And then that's going to give you a final answer of 2.64. Okay, so all that to say is that if you have a 0.3 molarity solution of acetic acid, the pH is going to be 2.64. You can automatically calculate what the pH is. And that tells you how acidic or how basic a concentration or solution will be. So now you can go home and calculate the pH of your vinegar, if that so interests you. Teaching you guys everyday skills that you'll need. All right. Any questions? We're gonna be doing a bunch more of these. Okay, let's move on then to the next problem. We're gonna be going on to 12.32. A. Okay, so I'm gonna have you guys try this on your own. But before I let you guys go, let's do the first step together just so that we get started on the same page, okay? So the first step is we want to write the equilibrium reaction basically. So it says that we have a solution of 0.2 molarity HCN. So we're gonna write HCN and we're gonna assume this is aqueous. It's going to be an equilibrium. So here we're just separating the H plus from the conjugate base. So it's going to be H plus and it's going to be Cn minus. Okay, so this is going to be your equilibrium that we're going to be working with. Okay, and then we're going to have to set up an ice table for this. Just make sure you guys get that down. I believe that's step 3, but just giving you a heads up. And so I'll give you guys about 3 minutes. And I want you guys to try calculating the pH of the solution. Now, if you guys notice right here, it's another hint. The exponent for the Ka is a lot less than 10 to the negative 4. So you can assume the 5% rule. So you don't have to do the quadratic equation. You can just assume that the change is negligible. Okay. All right. So I'm going to give you guys 3 minutes to try it out, and then we'll go over it together. So feel free to work together, guys, and good luck. Alrighty, guys, I'm going to start going over this, but if you're finishing up, please feel free to finish up and just check your answers as we are going along, okay? All right, so for this problem, we can start filling in, or before we start filling in our ice table, we want to just write the equilibrium constant expression. So we know that Ka is going to be the products divided by the concentration of the reactant. So it's going to look something like this. And that's going to be equal to 4.9 times 10 to the negative 10. Okay, now we're going to start filling in our ice table. Our starting concentration of acid was 0.2 molarity. And then we're going to start with none of the H plus and the conjugate base. We're going to lose some of the weak acid, which will give us an equilibrium concentration of 0.2 minus X. And then we're obviously going to gain in proportion to that. So it's going to be X and X. So it's basically the same setup as the previous problem. All right, now we're just going to plug it into this formula right here. So on the top, we get X times X, which is X squared, divided by the concentration of the weak acid, so 0.2 minus X, and that's all going to be equal to 4.9 times 10 to the negative 10. So far, so good? Okay, afterwards, I told you guys already, but you'll notice that the exponent for the Ka is less than 10 to the negative 4, right? A lot less. And so we can use the 5% rule, so we can ignore the change. And so we'll get an expression that looks like this. X squared divided by 0.2 is equal to 4.9 times 10 to the negative 10. So from here, it's a very simple calculation. We're just going to multiply by 0.2 on both sides. It'll cancel out here, and then we'll get X squared is equal to this right here. And if you simplify this expression, you should get a value of 9.9 times 10 to the negative 6 for X. Did I do that correctly? Gotta make sure now. I always look for if your eyebrows furrow or not. If they furrow, I know I made a mistake. Okay, so we're gonna plug in X for the H value, and then from here it's very easy. We got the pH formula, negative log of the concentration of H plus, and that's just gonna be the value for X. So we are going to get a pH of exactly 5, or very close to 5. Okay. So hopefully not too bad. We're taking a lot of things together. We're doing stoichiometry, equilibrium, ice table, equilibrium expression constant, and pH, and putting it all into one problem. Okay. Stop throwing your eyebrows for no reason. Because you're like, okay. So let's move on to the next problem. I said earlier while you guys were working that it's going to be a long one, and it is. But again, it's the same thing we've been doing, just combining it all together. Just more different nuances to it. Okay, we're going to skip this one right here, but it's a good practice problem if you ever want to try it. Okay, Now, before we move on, one thing I want to tell you guys, this is a long piece of text. So I'm going to just explain it, kind of paraphrase it for you guys. But basically, as you increase the acid concentration, the percent ionization is going to go down. That's basically what this is telling you right here. Okay. As you increase the concentration of a weak acid, right, the percent ionization is going to break down. Okay. So let's think about why. Let's say I have my weak acid. I'll just say HA. And then it's breaking down, right, into H plus and A minus. Okay. If I increase the concentration of the acid, okay, so I'm increasing the concentration right here. Remember the chandelier principle? If I increase the concentration here, what does that do to the other side of the reaction? Yeah, it's going to decrease it, right? Okay, and that's because it wants to maintain that balance with one another. It's going to have the opposite effect. And so what's going to happen is, remember the percent ionization? The amount of this right here that's going to break down is going to go down. So let's, right here, it tells us that I don't know what this is. Let's just say, assume this is 0.001. At 0.001, it has a 6% ionization. But as you increase the concentration, it's going to go down to less than 2%. And then you push it even further, it's going to be like let's say this is 1.2%. And then as you push the concentration more, the percent ionization is going to go down. Okay, so if I paraphrase everything we talked about here, basically, if you increase the concentration of a weak acid, the percent ionization is going to go down. Okay, and it's because of the chandelier principle. Okay. Make sense? Show. And then if you want to read the amazing text that I wrote down up there, my story, you guys can read it. But this is the summary of that. So I'll give you a second to write that down, but just to kind of preview what we're going to do next, the next problem we're doing is we're going to mathematically prove this. We're going to prove that as we increase the concentration, mathematically it's going to decrease the percent ionization. Any questions about this? All right, if not, let us move on. Okay, so we're going to jump right into 12.33. Now, I'm going to do the first part for you, and then after that, I'll have you guys do the second part. But if you guys take a look at the problem, it's asking us calculate the percentage of HF molecules ionized. So here, we are looking for the percent ionization. Okay, and if you guys remember, it is the concentration of H plus at equilibrium divided by the concentration of the weak acid initially. Okay, this is, and times 100%, sorry. Okay, and you're going to be doing this 2 times. You need to find the percent ionization for a 0.1 molarity HF solution and a 0.01 molarity HF solution. So if you guys feel confident doing this, you can kind of just ignore me for a little bit and just solve out the problem. But I'm going to do part A for you guys, just so that you guys have something to go off of. Okay, so we want to look at each solution separately. So first I have an HF solution, so I'm going to write the equilibrium. Okay, it's going to break down to H plus and F minus. And I'm going to set up an ice table, because we always love ice tables. Okay, and what I want to do is, in order to find the percent ionization of this compound right here, you need 2 things. Okay, the first thing that you need is the H plus at equilibrium. So we want whatever is going to be in this box right here. The other thing that we want is the initial concentration of the weak acid. So we're going to want these 2 boxes right here. So these are the 2 numbers that we really care about. And so just make sure you guys keep that in mind, because those are the 2 variables we need to solve for percent ionization. Okay. All right, so one of them we have already, and the first one is going to be the initial concentration of the acid. For part A, it's going to be 0.1. So we're going to write 0.1 molarity. And then same thing as usual, we don't start with any H plus or F minus. We're going to lose some of the HF to get 0.1 minus X. We're going to gain the same value for the product side. So we're going to end up with X and X. So if you guys notice, this is the same thing that we've been doing. Nothing's different. It's the same ice table. Okay, now we can plug this into the equilibrium constant expression. So we know that Ka is equal to 6.8 times 10 to the negative 4. And that's going to be the products. So X times X, X squared divided by 0.1 minus X. So I'll pause right there. Any questions so far? Yeah, what's up? No, so that's what I was going to get to. You're going to have to do the quadratic formula for this weak acid. So HF is kind of weird because it's a weak acid, but it's one of the stronger ones. But for part A, I'll give you the answer for X. But when you guys do part B on your own, I'll have you guys do the quadratic formula. Okay, so yeah, good catch on that. Since it is 10 to the negative 4, you can't assume the 5% rule. Okay, so you would have to use the quadratic formula here, but let's save you guys some time. And let's pretend I did the quadratic formula. So X equals negative B plus or minus the square of B squared minus 4AC all over 2A. Okay, and that's going to give us a value of 7.9 times 10 to the negative 3 molarity. Okay. And this is going to be the value that we plug in for X right here. Okay. So based on that, we can find the percent ionization. All we need to do is plug it into this equation right here. So the percent ionization is going to equal the concentration of X at H at equilibrium, which is the X number. So 7.9 times 10 to the negative 3 divided by the concentration of the weak acid initially, so 0.1 times 100%. And I'm going to leave it at that. I'll let you guys calculate the percent ionization. And then after that, what I want you guys to do is try part B on your own. I want you guys to do the same thing, but this time I want you guys to find the percent ionization for a 0.01 molarity HF solution. I know this is too much, huh? All right, so I'll give you guys about 4 minutes to try that out. Feel free to work with the person next to you to check your answers or even collaborate. And then after 4 minutes, we'll go over the answer together. All right, just a heads up, like Great mentioned, we do have to use the quadratic formula. Okay. So if you guys are still working on it, please feel free to finish up, but I'm going to start going over it because we do need to pick up the pace a little bit. Okay, so for this problem, if we start plugging the values that we got 0.01 molarity for HF, and then obviously 0 minus X plus X plus X. We got 0.01 minus X and then XX. We can plug in what we have into the Ka formula. So the Ka is 6.8 times 10 to the negative 4 is equal to X squared divided by 0.01 minus X. Now, like we said, we need to use the quadratic formula here. So I'm going to skip all this, and you're going to have to kind of trust me I got the right answer. But for your X is going to equal to 2.3 times 10 to the negative 3. Okay. All right, so this is going to be the concentration of H+. So if we plug these guys all into the percent ionization equation, we should get an answer, or we should get a formula of 2.3 times 10 to the negative 3 on the top, divided by 0.01 times 100%, and we'll get a final percent ionization of 3.873%. That's going to be your final answer. And for part A, the final answer should have been 23%. Okay, so as you guys can see, as we change the concentration, did I get the wrong answer? Let me double check. Got 3%. 2.3 times the negative 3 divided by 0.01. Oh, that doesn't even make sense. Wait, hold up. Did I get the wrong answer again? Oh, sorry. I was looking at the wrong thing again. Sorry, this one, you should have got, sorry. I'm looking at the wrong problems, guys. That's what I get when my handwriting's so bad. Okay, so for part A, you should have got 7.9%. Sorry. Don't judge me, please. You guys are judging me, and you guys deserve it. And then this one, you should have got 23%. That doesn't even make sense, dude. Come on, Mr. O. What are you doing? Get it together. Yeah, 7.9 and 23. Okay. Which makes sense based on our graph, right? I'm so dumb. I just talked about the principle too. So as you, what is it? Increase the concentration of the acid, right? It's supposed to decrease. And so right here, this is a weaker concentration, which means it should naturally have a higher percent ionization. And as we increase the concentration, the percent ionization goes down. Okay. I'm sorry, guys. I'm like looking at different problems right now. Okay. All right, so I'll give you guys a minute to kind of look at that, double check your work, absorb the information. But do you guys have any questions on any of it? I skipped the whole quadratic thing just because that's the math part. And I'm kind of assuming that you guys are able to solve the quadratic equation at this point. Okay, we're gonna take a quick 5-minute break. During that time, feel free to go to the restroom, just kind of relax, stand up. But if you want me to go over any part of the question, we can do that during the break as well. But don't feel obligated to listen to that if you don't need it. So let's take 5 minutes and then we'll come back together and move on. Okay, so we are going to skip the next problem. It's kind of similar, percent ionization and things like that, but we're gonna move on to the next topic. So we're gonna be talking about polyprotic acids, okay? So before we move on, I want you guys to kind of think back at how acids work, okay? Regular acids. Okay, so regular acids, the general formula we've been looking at are acids that give up only one hydrogen, right? So we've been looking at acids where we give up a hydrogen and then we got the conjugate base, right? Okay, but now we're going to be looking at acids that have multiple hydrogens that they can give up. Okay, that's what a polyprotic acid is. Okay, polyprotic acids are acids that have more than one ionizable proton. If you want to kind of put it simply, the way I like to say it, they can release more than one H+. Sometimes they can give up 2, sometimes they can give up 3. Okay, that's what a polyprotic acid is. Poly means many, protic, proton, acids that give up many protons, more than one. Okay, the concept makes sense, right? Okay, all right. Now we're going to look at an example because even though the concept is very simple, the math gets really annoying, okay? And I'll show you guys why. So here we have a polyprotic acid. Our acid is H2SO3. And as you guys can kind of guess, it can give up an H, and then we get the conjugate base, right? And if you guys notice, we have a Ka for this equilibrium. But if you guys notice, it says Ka what? 1. This is the first ionization. Because if you guys notice, this acid can release an H+, and it gives up a conjugate base, right? But if you look at this conjugate base, what do you notice about it? It also has an H, which means this guy right here, HSO3 minus, can also go into equilibrium to give up SO3 2 minus and H+. So that's what a polyprotic acid is. It's an acid that can make a conjugate base that can also act as another acid. Kind of annoying, huh? And as you guys might guess, if there's a Ka1, there is a Ka2. So the number is different for the second ionization because HSO3 minus is a different acid than H2SO3, which means that it's going to have its own unique equilibrium constant. Does that make sense, guys? Hopefully it does. Okay, I'll give you the value for Ka2. It's underneath it, but I kind of can't show everything at one time. But Ka2 is going to be 6.4 times 10 to the negative 8. Okay, so what that shows us is that as we have multiple successive ionizations, the Ka is going to get smaller, which means that as you give up more hydrogens, it's going to want to give up hydrogens less. So this guy wants to give up hydrogen a lot more than this guy down here. Okay, this is a stronger acid than its conjugate base. Okay, so just keep that in mind. It is always easier to remove the first proton than the second, and the second is easier than the third, and so on and so forth. You'll rarely ever see one with 4 ionizable protons. It's usually going to stop at 3. Okay. Yeah, what's up? Oh, that's going to be a Ka2, sorry. The Ka2 is 6.4 times 10 to the negative 8. Sorry about that. That arrow was very confusing. Okay. So just keep that in mind. Some acids like to give up multiple protons, but as it gives up protons, it wants to do it less and less. Okay. Any questions about that? Guys chilling? Okay, so that's polyprotic acids. Now, I want to give you guys a heads up about one specific example of a polyprotic acid that you'll see quite often. And it's one of my favorite compounds because it's the one that burned me in college. But the notable example is this guy right here, sulfuric acid, H2SO4. And I want you guys to write that down because sulfuric acid is interesting because it is a polyprotic acid, but it's a strong acid. So sulfuric acid is a strong acid, which means it doesn't have a Ka because it has almost complete ionization. So it's not in equilibrium. Okay, it breaks down completely. So if you have 1 mole of sulfuric acid, you're going to get 1 mole of H plus and 1 mole of the conjugate base. Okay, it's a strong acid, complete ionization. However, once it breaks down into HSO4 minus, right, we got it right here, this guy is a weak acid. So this guy right here has an equilibrium constant. Okay, so this is why this is an interesting example. It's because the first acid, right, the full neutral acid is a strong acid. But once it gives up a proton, it becomes a weak acid. The conjugate base is a weak acid. And so we need to keep in mind the Ka value. So the property is going to change. Okay. So just wanted to give you guys a heads up about that. If you have a strong acid that's polyprotic, the first step is going to be complete ionization. But then after that, it's going to be an incomplete ionization. Okay. Just keep that in mind. And I think that's the only polyprotic. That's the only polyprotic strong acid, but let me double check. Yeah, that's the only polyprotic strong acid. This guy's the only one that has multiple hydrogens it could give up. Okay, just keep that in mind. I also have a scar on my elbow from this because my lab partner bumped into me with sulfuric acid. Yeah, what's up? Yeah, it's the conjugate base and it's also a weak acid. Yeah. Okay, you guys ready to try a problem with these polyprotic acids? Sounds like fun, huh? Just a heads up, we're doing multiplied tables again. And actually, this isn't the last one. Okay, so let's go to 12.35. If you guys think you guys can solve this out on your own, please feel free to do that. I highly recommend trying out these problems. Even if you get it wrong, the process is what's important. So I recommend you guys try it, but I'm going to slowly go over it step by step. But if you want to try it, you can kind of just ignore me. Let me talk to myself while I'm going over it. Okay, so the solubility of CO2 in water at 25 degrees Celsius and 0.1 atmospheres is 0.0037 molarity. Okay, and we can assume that all the dissolved CO2 is in the form of carbonic acid, okay, which is produced in the reaction below. Okay, first thing we want to try to find is the pH of this solution, okay? So the acid that we're making here is H2CO3. So for part A, the compound we're going to be trying to find the pH for is carbonic acid, H2CO3. Okay, now we know it's an acid, so if we want to find the pH, we need to find the concentration of H plus at equilibrium. Okay, so if we want to write the expression for carbonic acid's equilibrium, it's going to be this. It just releases one proton. Okay, and then from here, if we just want to find the pH, we need to find the concentration of this guy at equilibrium. So we need to write an ice table. I'm sure you guys are sick of ice tables now. It's ice, baby. Okay, it tells us the concentration of carbonic acid is 0.0037. So we're going to do 0.0037. Okay, same thing as normal. We know that there is no H plus and no conjugate base in the beginning. Same as usual, we're going to increase and then we're going to decrease with the same values. So we're going to get 0.0037 plus, oh, sorry, not plus. I'm so dumb. I just reversed this. I'm telling you guys, I'm getting dumber as I get older. Minus X. Okay, and then we got X and X. All right, so from here, we can just plug it into the equilibrium, the Ka expression. Okay, so Ka1, right? This is the first acid that it gives up, or the first proton it gives up. So Ka1 is going to be 4.3 times 10 to the negative 7 equal to X squared on the top divided by 0.0037 minus X. Now, if you guys notice, the exponent is less than -4. So that means we can ignore the change because it's going to be insignificant. And so we're going to have this as our expression. 4.3 times 10 to the negative 7 times 0.0037 is equal to X squared. And then if we simplify that value, we should get X is equal to 0. I'm looking at the wrong question again. Sorry. X is equal to 4 times 10 to the negative 5 molarity, around there. I'm gonna double check because I don't even trust myself anymore. Yeah, I'm wrong. Wait, hold up. Never mind, I'm right. Okay. Man, I'm like really second guessing myself. So 4 times 10 to the negative 5. I'm sorry, guys. Clearly, I didn't wake up. Okay, so that's going to be what we put in for the concentration of H plus at equilibrium. So from here, we just need to plug it into the pH formula. So pH is equal to the negative log of the concentration of H plus, which is going to be 4 times 10 to the negative 5. That'll give us a pH of 4.4. So that first part's pretty easy, right? Literally the same thing that we have been doing. So the answer to part A is 4.40. Okay, now we're gonna add in the polyprotic acid part. So if you look at part B, it's asking us what is the pH concentration of CO3 2- in the system. So now it's asking us to find what is the concentration of CO3 2-. Sorry, not the pH concentration. It should just be concentration. Okay, so in order to make CO3 2 minus, what we need to do is look at the conjugate base right here. Okay, HCO3 minus. You'll notice it has a ionizable proton. So HCO3 minus can give up a proton to form CO3 2 minus. Everyone see that? Okay. So that means in order to find the concentration of CO3 2 minus, we need to do another ice table to see the new equilibrium concentration. Okay, however, actually, you know what? You guys can try filling out the ice table first. Don't do the calculations. Don't try to calculate for it. I just want you guys to fill in the ice table with the X's. Okay. So I want you guys to fill in this ice table. Don't do the calculations yet. I just want you to see if you can fill it in with the, you know, the X, the plus X, the minus X, things like that. Don't solve for X yet. So I'll give you a minute to do that. Okay, so for this ice table, it might be a little bit confusing because what we need to do is we need to take the values from the first ice table and plug it into this new ice table. So if you, let's start with the top left corner. So HCO3 minus, what's the concentration of HCO3 minus initially? Yeah, good catch on that. It's gonna be the value for X because this is what we end up with, 4 times 10 to the negative 5. So our initial concentration is 4 times 10 to the negative 5. Okay, now you might just out of habit try to put 0 and 0 here, but the only 0 we have is this guy because we don't have any starting number of CO3 2 minus, right? It hasn't broken down yet. However, we do have some H plus in the system right now, right? How much H plus do we have in the system? Yeah, same thing, 4 times 10 to the negative 5. And so this is what makes polyprotic calculations a little bit trickier, is because we need to take into account what happened in the first ionization and then bring it into the second ionization, okay? So just to reiterate, when H2CO3 broke down, it broke down into 4 times 10 to the negative 5 for H plus and HCO3 minus. That's where we get these values. Okay, from there, we want to do the same thing. We're going to lose some of the weak acid, and we're going to gain H plus, and we're going to gain CO3 2 minus. Okay, which means for our equilibrium values, we're going to get 4 times 10 to the negative 5 minus X. We're going to gain the same amount for X. And then what we're looking for is this right here. X is going to be the concentration of CO3 2 minus. Okay, so that's how we set up our ice table. And then from here, it gets a little bit more annoying with the Ka calculation. So let's plug this into the Ka formula. The Ka2, the second ionization, is going to be 5.6 times 10 to the negative 11. Is equal to the concentration of the products. So 4 times 10 to the negative 5 plus X. Hold up, yeah. And then times X divided by 4 times 10 to the negative 5 minus X. Okay, now this looks like a very ugly fraction to solve for. Okay. However, if you guys look at the Ka, what does that let us do? Yeah, we can skip the change. So the two changes were the change to the HCO3 minus, so the minus X, so we can get rid of the minus X on the bottom. Okay. And then we still want to know the change for H plus, right? Because that's what we're solving for. We want to see how much the H plus changes. And so what we want to do is we want to keep the plus X. So we're only going to be getting rid of actually, hold up. No, we're going to get rid of both changes. We're looking for CO3 2 minus, sorry. If we were looking for H plus, then we would have to take into account the change. But if we're looking for CO3 2 minus, we can get rid of both changes. Sorry about that. Okay, because if you don't, you'll get the same number for H plus, and you don't want that. Okay, so from here, the math actually gets really easy. What do we have on the top and bottom of the fraction? Yeah, the same value, so you can cancel out. So we're done. X is going to equal 5.6 times 10 to the negative 11. And that is going to be the concentration of CO3 2-. So even though we canceled out everything, and this is just the Ka2 value, it's because it's an approximation. It's just super duper close. It's within that 5% rule. Make sense? Okay, however, if I wanted to find, let's change this question. If I wanted to change the concentration for H plus, we would have to do things a little bit differently. Okay, so you guys don't need to erase it. I'm going to erase it just to show you guys. But what we would want to do instead is we want to, hold up. I'm going to rewrite the equilibrium expression. So I'll have 4 times 10 to the negative 5 plus x times x, negative 5 plus x times x, and on the bottom, I'll have 4 times 10 to the negative 5 minus x, okay? So we got rid of both changes when we were looking for CO3 2-, right? But if I wanted to find the H plus, I can't get rid of this change right here. I can't get rid of plus x, because if I do that, I'll get the same number as the first ice table, right? So if I'm looking for H plus concentration, I can only get rid of the change for the weak acid. So I'll get rid of the minus x on the bottom, but I would keep this x right here. Okay, so if I rewrote the equation, it would be 5.6 times 10 to the negative 11. And that's going to be equal to 4 times 10 to the negative 5x plus x squared. And then at that point, you would have no choice but to use the quadratic in order to solve for the concentration of H plus. So we're not going to do that today, but just giving you guys a heads up. If you were looking for the H plus concentration, you can't get rid of the change of the H plus, okay? Because they're going to want a different value than the one that you had. It's going to be a very small difference, but they're still going to want to see that difference. All right. All righty. So we got about 10 minutes left. And in that time, I want you guys to try the last problem. Okay, 12.36. And that'll be the last one for the day. I want you guys to do basically the same thing. I want you to calculate the pH of this compound right here. I gave you the Ka values. It's basically the same thing that we did. And 10 minutes is actually the perfect amount of time, because that's about how much time you should be spending on each FRQ question on the AP test. So kind of consider this as a little check to see if you understand how to solve these problems. Okay. So I'll give you guys about 10 minutes to solve it. I'm actually going to write the final answers for you, just so you guys can check your answers in a couple minutes. But yeah, try it out. See if you can get the correct answer. And then, yeah, I'll give you the final answers in a sec. So good luck, guys. Alrighty, guys. So I know you guys are still working, and I'm going to let you guys go in a bit. But I have the answers up there if you guys want to check your answers. Of course, this is being recorded, so it will be online. But if you want to take a picture of it, feel free to take a picture of it as well. Just make sure you guys are doing it correctly and you have a good understanding, okay? So yeah, that's pretty much it. Give you guys a couple more minutes to finish up your problem, but I'll dismiss you in a few minutes, okay?